So what we're going to look at next in terms of talking about distributions is what's known as a normal distribution. So we've done some different things looking at different types of density curves, and we've paid some special attention to some different things involving the density curve that goes around a graph that's roughly symmetric, that looks like a bell curve. And what we refer to those graphs typically are what are known as normal distributions. So some different things about a normal distribution, and here's just two examples of some different things involving normal distribution. So very similar to a graph that's roughly symmetric, you have the center of the graph with sort of its highest peak in the center, and then as you go away from the center, the graph starts to, or the frequency of the graph starts to kind of go down a little bit. So these are just two examples of different normal curves, and a normal curve is drawn around a graph that's roughly symmetric. And this curve that we're drawing around here, it's sort of a bell shape type thing. So just some different things notation wise that we have on the normal curve, and that is the mean is the line here, and the mean is what separates the normal curve into two equal halves. And then what we're basically going to do with the normal curve is we're going to break this up into sections, and the sections, the distance of those sections between each of the two sort of endpoints there, we break that up using the standard deviation of the data. So if we kind of move into different things that we know about a normal distribution. So the mean of the normal distribution is the center of the normal curve, and that's what we're using when we're talking about a graph that's symmetric. The standard deviation here is the distance from the center to the change of curvature points on either side. And rather than writing normal distribution every time we start to talk about a normal distribution, we're going to abbreviate with it this right here. And what this will describe as the N describes the normal distribution, and then this right here speaks to what the mean of that normal distribution is. This right here speaks to what the standard deviation of that normal distribution is there. So that's just some notation things that we're going to look at with this. So a couple things about normal distributions. One, they're very good at describing distributions involving real data that comes from some type of application. They're also good for approximations, and we're going to take a long look at approximations with these today. And a lot of the procedures for inference, which is basically the procedures that you follow to make predictions on data that you collect, a lot of the procedures that we're going to follow are based on the normal distribution. So I would say if there was one thing in statistics that I would tell you that is the most important, I think you'd have a hard time arguing that the normal distribution wouldn't be at the top of or very close to the top of that list. Very important for a lot of the things we're going to do moving forward. So in terms of the normal distribution, so just keep in mind with any type of density curve, whether it's normal or otherwise, the area of the density curve always equals 1. That's this right here. So there's this whole business of what's known as the empirical rule. And the empirical rule is just some things we know that are true about the normal distribution. So when you have a normal distribution with the mean down the middle and a standard deviation value, here's what we know that is true about the normal distribution. We know that 68% of most data values in a distribution that's normal will fall within one standard deviation of the mean. And that's basically this area in here, from here to here. Some other things we know. 95% of the data values, or approximately 95% of the data values in a normal distribution, will fall within 2 standard deviations of the mean. So that's basically from here to here. And then you have finally this, and we know that approximately 99.7 of the data values in a normal distribution will fall within 3 standard deviations of the mean. So that's from here to here. So just to kind of show you from the diagram what we're talking about here, 68% of the data falls in that sort of area. So the area of this part of the curve, remember the whole area is 1, is 0.68. Some other things we know, right? 95% of the data is going to fall from here to here. So we know that approximately the approximate area of the curve that runs from here to here is about 0.95. And then finally we have this. So the area under the normal curve that goes from all the way up here to all the way back down here is approximately 0.997. And we're going to use those percentages, along with some other sort of things that go with this, to do some different things involving inference, to take some data, collect it, and use it to make some kind of prediction about something here. So here's an example of a problem involving the normal distribution. So the question says, the distribution of Iowa test of basic skills vocabulary scores for 7th grade students, Gary, Indiana, is close to normal. Suppose the distribution is normal with a mean of 6.84 and a standard deviation of 1.55. Sketch the normal density curve for this distribution. So what we're basically asked to do here is we're asked to make a normal curve with 6.84 going down the center, and then we're going to put our points of curvature on the graph in increments of 1.55 from the mean. So what you would get for part A is something that looks like this, right? So I got 6.84 down the middle, and then I'm just adding 1.55 to each one of these data values here, here, and here. And then going in the to the left, I'm going to subtract 1.55. So I'm going to start with the 6.84. I'm going to keep subtracting 1.55, and that's where those data values come from there. So that's the density curve for this particular distribution. Now I'm going to use this density curve to answer some questions involving the normal distribution. So part B says, what percentage of scores are less than 3.74? So 3.74 is right here on the normal curve, and what we know is that 3.74 is 2 standard deviations from the mean. Here's 1 standard deviation from the mean, here's 2 standard deviations from the mean. And what we know about that is 95% of the data falls somewhere between here and here. So what that means is 5% of the data falls outside this window here, and it's equal on both sides. So this would be 2.5% over here. This would be 2.5% over here. So if we're talking about the scores that are less than 3.74, that would be this area here under the normal curve, which is approximately 2.5%. So that's the answer for part B there. And then part C asks, what percent of the scores are between 5.29 and 9.94? So when I take this here, we're basically looking at 1 standard deviation below the mean versus 2 standard deviations above the mean. So there's a couple different ways to kind of look at this. One of which would be to say that if 68% of the data falls from here to here, here to here, that means each one of these sections here would be 34%. So this would be 34%. This section here would also be 34%. So 68% covers this area right here. So what I'm then looking to figure out here is what percentage of the data is going to fall in this sort of area here. So one of the things that you can look at, and that's what I'm sort of referencing over here, is this 9.94 value is 2 standard deviations above the mean. So the area under the normal curve that goes from here to here is 95%. It's 0.95. So if you were to just take the 95% and subtract this piece here, this 68% that's in the middle, that's going to give you the area for these two sections here, this section and this section. And if you take that and divide it by 2, that's where the 13.5% comes from. And there's a couple different ways that you can do that, but I think that's probably one of the easier ways to sort of look at this. So before we kind of go to before we go on to the next part of this, I want to just show you something just kind of real quick here. So let me pull this up, and I'm just going to draw myself a density curve. And you might want to just maybe make a note of this off to the side, but I think this would be helpful for what we're going to do moving forward. So if I just take this here, and I'm just going to draw myself what will probably amount to a very poorly drawn bell curve. That's not too bad. So I got my mean down the middle, and then I got one standard deviation from the mean. I'm just going to sort of approximate this here. So here's one standard deviation from the mean. So we know that from here to here, 68% of the data is going to fall. So since these two sections here are both the same, this section here is going to be 34%. This section here will also be 34%. And if I go a second standard deviation from the mean, something like this here, we know that from here to here, 95% of the data is going to fall. So if you take just the percentages here on this, if I did 95% minus 68%, that leaves you with, in each of these two sections, 27% total. And if you cut 27% in half, you get 13.5%, which is what's going to go here. And then, if you go a third standard deviation from the mean, which would be here, and this would be from here to here, this is 99.7%. So if I take 99.7% and I take out the 95%, these two sections here put together will be approximately 4.7%. So that would make this 2.35%, and that would make this here 2.35%. Which basically means that everything that's outside here, going in this direction, going in this direction, if 99.7% of the data falls between here and here, that leaves me with 0.3% to fall here and here total. So if you take 0.3% and you cut it in half, that's going to make this 0.15%, and that's going to make this, I'll just put this up here, 0.15%. So I think having each of the sections sort of blocked off by percentages is very helpful in terms of being able to answer questions about the normal curve that involve this type of setup here. So just kind of moving forward, you have this checkpoint question here. So the distributions of height of young women aged 18 to 24 is approximately normal, with a mean of 64.5 and a standard deviation of, back up the truck here, and a standard deviation of 2.5. And the question basically says here to sketch a normal density curve for the distribution of young women's height. So you're going to try to make yourself your own density curve and then label it 1, 2, and 3 standard deviations from the mean. So why don't you take a moment and try to answer these checkpoint questions on your own. So the normal density curve that you have should look something like this here. So if you put the percentages in here, that's probably not a bad idea, although it's not something that you have to do. But what you want to have here is your 64.5 down the middle, Okay, that's your mean. And then I'm just going to add 2.5 going to the right. So I get the 67, the 69.5, and the 72. And then going to the left, I'm going to just subtract 2.5 each time. So that's where you get your 62, the 59.5, and the 57 from, with those there. So that's what your density curve should look like. And here's the thing, you need to draw this correctly in order to answer this sort of the application questions that come after this. So question number 2 says, what percent of young women have heights greater than 67 inches? So if you go back to your curve, here's 67. And if you recall, this right here, this was 13.5, right? And then you had 2.35 here. And then you had the 0.15 on the end, which if you add those percentages together, okay, you're going to get about 16%. 16% of young women in this particular normal distribution have heights that are greater than 67 inches. And question number 3 says, what percent of young women have heights between 62 and 72 inches? So if we come back to this here, let me kind of erase this stuff here. So we're basically talking about what percentage of the data falls from here to here. So if you take your percentages from, this would be 68% in the middle, you got your 13.5 here, you have your 2.35 here, and if you add all those together, what you're going to get for this is approximately 84%. So in this particular distribution, approximately 84% of young women have heights that are somewhere between 62 and 72 inches there. So some different things with the standard normal distribution. So one of the things that is helpful to do when you're talking about normal distributions is to know what the z-score is for a given value. And one of the things that made some of the questions that we've done with the normal distribution pretty easy for the most part up to this point has been, we've been talking about approximating values, and I'm kind of just taking you back to this here. We're approximating values that are labeled on this curve. So that's not always the case. Sometimes we take a look at some different things that might ask you, what percentage of the data falls between, say, 60 and 69, like that, where you have data values that aren't labeled on your horizontal axis. And what do you do in order to figure out what the percentage of numbers is that falls in between, say, those two values? So one of the things that's helpful to know when you're doing something like that is what the z-score is for a given data value or data value. So keep in mind, and we talked about this the other day, of how whenever you have a group of z-scores, the mean of those z-scores is always 0, and the standard deviation for a group of z-scores is always 1. So anytime we're talking about z-scores, remember that those two things are always going to be true. So there's a couple different ways that we can use the normal distribution to make approximations, one of which is what's known as the standard normal table. So in the back of your textbook, there is what's known as the standard normal table. And what that will give you is, if you have a z-score for a data value, it will give you what the approximate area is under the normal curve that would be below that given point. Your calculator also has a standard normal table, and that's really what I want to sort of speak to you more about here. So here's a z-score of 0.81, and what we want to know is what percentage or what area under the normal curve falls below, since it says less than, falls below a z-score of 0.81. So remember what we said about z-scores. If you have a positive z-score, that means you're talking about a data value that's above the mean. So if you come back to this table, or this density curve here, 0.81 might be somewhere like, I don't know, right about here possibly. So when we talk about z being less than 0.81, what we're basically saying is, what's the area under the normal curve that encompasses that section there? So 0.81, if you notice, it's not one of the whole number values in terms of the standard deviation goes. So how am I going to figure out the answer to that? So there's this, what's known as the normal CDF in your calculator. And when we're looking at the normal CDF, we're sort of using this normal CDF in place of this standard normal table that's in the back of your book. So the answer to this is 0.7910. About 79.1% of data values fall below a z-score of 0.81. So where does this number come from in regards to your calculator? How do I know that the area here, this gray section here, how do I know that that really is 0.7910? So let me kind of exit out of here and you go to your calculator. So if I pull this up, and what I want to do here is to get the standard normal table in your calculator is you want to push second and this vars key right here. And when you do that, you get this, we're looking at the second line down, it's what's called the normal CDF. So in order to answer this question, what we're basically looking at is the area under the normal curve that's less than 0.81. So keep in mind that what that basically means in terms of a lower bound and an upper bound. The upper bound here, because we're talking about less than, is going to be 0.81. The lower bound is essentially, because the density curve is going to go infinitely in both directions, but in this case it's going to go infinitely to the left, we're basically saying that this is going to be negative infinity. So the way you put negative infinity in your calculator here is I just want to do negative E99. And that's what we're going to use from a calculator standpoint. That's what we're going to use to represent negative infinity. So if I come down here to paste, you want to leave this at 0, you want to leave this at 1, because like I said, when we're talking about z-scores, the mean for a group of z-scores is always 0, the standard deviation for a group of z-scores is always 1. So then I want to paste this in, and I'm going to push enter, and that's where the 0.7910 value comes from with that type of thing there. So the standard normal curve in your calculator, much easier to use than the one that's in the back of your book. So I highly recommend that you get very familiar with this whole business of the normal CDF because it's just going to make things a lot easier for what we're going to do moving forward with the normal distribution. So let me come back to this here and go over some other things. So if we wanted to take a similar question, but instead of saying what's the area under the normal curve that's less than a given value, what if we wanted to take a look at this and say, well, what about if you had a z-score of 0.8, which is what this is here, what would be the area under the normal curve that's greater than that, greater than 0.8? So here's the density curve that involves that. So here's 0.8, and I want to know what's the area under the normal curve that would be from here. So if we're talking about calculators, so if I come back to this here, all right, I'm going to do the normal CDF, so I'm going to go to second vars, I'm going to go to 2. So I'm going to put 0.8 in as the lower limit, and then if we're talking about greater than, we're basically talking about positive infinity. So positive infinity in your calculator is E99. So I'm going to leave the mean as 0, leave the standard deviation as 1, and when I paste that in there, that's where the 0.2118 comes from on your diagram there. So the normal CDF in your calculator, very good tool to get familiar with. So different question here, and this one says find the proportion of observations under the standard normal curve that have z-scores between 1.25 and 0.81. So what you get from this is a normal curve that looks like this. Here's negative 1.25, a z-score of negative 1.25. Here's a z-score of 0.81. And I basically want to know what's the area under the normal curve that's in here. So if I once again go back to my calculator and I put in the normal CDF, where the lower bound is negative 1.25, the upper bound is 0.81, So that's where that 68 or 0.685 value comes from there. So an example of some things with the normal curve, and it says here, use the standard normal table to find the value of z from the following standard normal distribution that satisfies each of the following conditions. In each case, sketch a normal curve with your value of z marked on the axis. So when we're talking about some different things here, and this is what's known as the inverse norm. So I'm going to kind of show you this here, and let me kind of back this up. So you have for this, hold on one sec here, whoops, a little too fast. So you have this whole business of what's known as the inverse norm. So this is the normal CDF. The inverse norm, okay, is on your calculator. So whenever you're going from a z-score to a percentage, that is what you want to use the normal CDF for. But if you have a percentage and you want to know what the z-score is for that given percentage, you want to do this whole business of the inverse norm. And I'm going to show you where that is in your calculator here in a moment. But the question here for number 1 says, what's the 20th percentile? So what it's basically asking you is if you have a standard normal curve, what would be the z-score at the 20th percentile? So if I wanted to answer that question here, okay, what I want to do is I want to go to my calculator, and I want to do not the normal CDF but the inverse norm, which is on the same screen as the normal CDF. So I push second vars, and if you look here, the third line down, this is the inverse norm. So the thing with the inverse norm is the inverse norm will measure the area under a normal curve that falls below a given percentage. So this part here, it asked me for the 20th percentile. So remember, percentiles measure the number of data values that are at or below a given point. So if I put 0.2 in here for the 20th percentile, just once again leave your mean and your standard deviation at 1, and I paste this in here, okay, that is negative 0.8416. So what that means as far as the problem here goes, what that's telling me is the 20th percentile has a z-score of negative 0.8416. So question number 2 says 45% of all observations are less than z. So I want to know what would be the z-score for a data value where 45% of the data values fall below that value. So essentially I'm asking what would be the z-score for the 45th percentile. So if I jump out of this and come back to my calculator again, and I go inverse norm of 0.45 now, and that's where this comes from here, this negative 0.1256, which is what this value is here. And then the last part, just notice it's a little bit of a different question because it says greater than. So if you have here 30% of all observations are greater than z. So I'm just going to kind of just draw real quick a little curve here. So you have 30% would be over here. So what we really want to know here is, in terms of using the inverse norm, I want to know what's the inverse norm of 0.7, because inverse norm only measures below a given value. So 30% above would be 70% below. And that's basically what this measures right here. So that's why I'm putting in 0.7 for this and not 0.3. So why don't you guys take a moment and kind of try and do this on your own. So it gives you some z-scores here, and it's asking you to sketch your standard normal curve and find the area under the normal curve for each of the given z-scores. And then there's another question here about the inverse norm. So why don't you take a moment and see what you could do with that on your own. So with number 1, you have these questions here. These are all normal CDF problems. So with number 1, I'm going to do the normal CDF from E99 from negative infinity to 1.39, and here's the value that you get when you do that, 0.9177. So that's the answer for the first one there. So the area under the normal curve that's below a z-score of 1.39 is approximately 91.7, 91.8% there. For part 2, what percentage under the normal curve, or what's the area under the normal curve that's greater than a z-score of negative 2.15? So I would do the normal CDF from 2.15 to positive infinity, and that's where the 0.9842 comes from. And then number 3, also a normal CDF problem. I want to know what's the normal CDF from 0.56 to 1.81, and that's what you get there. So just remember, normal CDF is used when we know what the z-scores are and we want to know what's the area under the normal curve based on those given z-scores. The other part of this kind of goes in reverse. So we have the percentages and we want to know what's the area under the curve, or what's the z-score for that area that's under the curve. So the 54th percentile, remember percentiles measure at or below a data value, so I just want to do for that the inverse norm of 0.54. That's where the 0.1004 comes from. So that would be the z-score for number 4. For number 5, once again, it's talking about less than, so I can just do the inverse norm of the percentage here. Right, so if I did the inverse norm of 0.8, I get 0.8416. And then notice for number 3, it says greater than z. So just real quick, just drawing this curve here. Right, if 32% of the data is here, that means that 68% is going to fall below that value. So that's why I'm doing the inverse norm of 0.68, which if you do that, you get 0.4677. So what we're going to look at next is some different things involving applications involving normal distributions. We're also going to take a look next at some applications involving some different things with the inverse norm as well.